Hello, today I'm going to review chapter 6 of Shigley's Mechanical Engineering Design book. The latest version of this book now is the 10th. For better understanding, I do suggest you to take the book if you haven't done that yet. All the graphs, tables, and figures that I'm going to show here and I'm going to refer to have taken from 10th version of Shigley's book. If you want to see more videos, feel free to subscribe this channel, and if you have any questions, you can comment it below, and if you think that you might need the notes, just send me an email at engineeringfun2016@gmail.com, and I'm gonna provide you the notes that I'm gonna use in this video. Before I want to start this chapter, I'm gonna have a brief review about solids, some part of solids that we may need in this chapter. If we recall from solids, if we have a specimen under axial loading like F, a stress for such a case can be defined as the amount of force over cross-sectional area. If I make a section here, like section AA, stress at section AA can be represented as force over area. This stress here is average stress at the section. So by that I mean if that's section A, stress at all points at this section are assumed equal and equal to F over A. If I had a hole here like that, if this section is far from A, stress at this section can again be represented as this equation. But if that's so close to the hole, and if it goes through the hole, like if I have a section like BB, stress at section BB is not equals stress at section AA. What important is for us in this chapter when we are talking about the stress, any type of stress, is not a stress at each point, is maximum stress. It doesn't matter if it's normal or shear. The maximum stress is important for us because we want to design something, and when you want to design something, the point that maximum stress happens at is important for us, and we want to know the maximum strength of the material. So if you want to find the maximum stress for this case, we need to find a stress at around the hole where there is a stress concentration. So sigma at section BB, the maximum stress, is again F over A, but we need to multiply that one by coefficient, which is KT. This means that we can just normally find the stress, and after multiplying by that coefficient, we're going to find the maximum stress around the hole. Okay, this KT is called theoretical stress concentration factor. Okay, in order to find that KT, we need to go to a table that I'm going to refer to that one down the road. That's the first point that I wanted to mention. Okay. The second point is about loads and stresses. We can have two types of stresses: normal stress and shear stress. Stress, by definition, is force over area, and we discussed about the difference between stress and pressure. Normal stress means, which we show with sigma, is when the load is axial, or when the load is axial, we can define that one. And for shear stress, that load is somehow not perpendicular to the cross section, is kind of parallel to the cross section and happening on the specimen, like that. Okay, we don't have any problems at this point. For loading, we can have different type of loading. We can have axial loading if that's our specimen. This is axial loading F. This type of loading causes normal stress, and the amount of stress is F over A. F is the amount of force and A is the cross-sectional area. So whenever at this chapter I'm saying stress, I mean maximum stress. Okay, so that's an agreement. Another type of loading that we can have is bending moment. For example, I have a specimen under this type of loading. I call this one M. A stress caused by this type of loading is again normal and can be written as M rho over I, where I is second order, second moment of inertia. Okay, if I look at this this specimen from this side, if I look at the specimen cross section, this rho is a distance of a point that we want to read the stress from the center. For example, if this is the point that we want to find the stress at, and that's the center, rho is this distance. So a stress at point A is the amount of bending moment times rho over A. Since we are looking for the maximum stress, so what maximum stress happens when, I'm gonna say sigma max happens when rho reaches to its maximum amount, which is radius. So maximum stress is M R over I. This is what's important for us. Okay, so this is the second type of loading. We can have third type of loading, which is torsion. For example, I have a specimen like this, and there is some torques like T twisting the specimen. Here I'm gonna have shear stress, and the amount of stress will be T rho over second polar moment of inertia, and the maximum stress, which is important for us, happens when rho is maximum, so that will be Tc over J. We can have fourth type of loading, which is shear force. For example, when we have a specimen like this and some force like V is acting, that force happens some stress, let's say VQ over I thickness and blah blah. Okay, if you wondered what this J and this I is, I is second moment of inertia, and J is second moment, second polar moment of inertia. These two can be found either online or at the appendix section A18. For example, for circular cross section, I, for circular without any holes is p d to the power of 4 over 64, where d is the diameter of the cross section. Like if that's like this, and this is the. For the other type of cross sectional, like for T beam, for rectangular one, and the other types, you can go just to this table, or you can find it online. We don't have any problems about this part. Okay, now we can go to chapter 6 and see what this chapter is about. It's about fatigue failure resulting from variable loading. Okay. So the first and important part of this chapter is about SN diagram. SN diagram is a log-log graph. So at the vertical axis, we have fatigue strength, SF, log of SF. And in the horizontal one, we have number of stresses, log of N. Okay. This is valid for a completely reversed stress scenario. I'm going to talk about this one down the road. Okay. There are 3 critical points at this graph. This is the first critical point. When n is equals to 1. We said that that's a log-log diagram, so 10 to the power of 0 is 1. Okay. That's the first important point. The second important point is somewhere here, when the cycle, number of cycles, or n equals to 1000. So I'm gonna say here, for example, I can delete this one, okay. And the third important point is about 1 million or 10 million cycles. These are the 3 important points for us. Based on these important points, this graph can be categorized in different regions. For example, whatever happens in the before the 1000 cycles is known as low cycle scenario here, and whatever happens after then is high cycle. Based on life, whatever before 1 million cycle is finite life, and whatever after is infinite life. For example, if I have a specimen like this, and if I put it under axial loading, this is what we recall from solids. If I want to draw a stress strain diagram of this one, if that's a ductile material, it will be something like that. We have sigma y, yield strength here, ultimate strength here, sigma ut, and fracture strength here. Okay, stress here. If I want to draw load, I'm gonna say ft diagram for that one. That means that we are starting to putting load on the material until failure happens. So the amount of load is this much. So after 1 cycle, failure happens. In this chapter, we want to say that failure can happen with less amount of force when we have a cyclic load. For example, we are increasing load like this, then we are decreasing load, then we are increasing load, and then, okay, fracture happens here. So at this point, the amount of force is less than our first scenario. So with less amount of force, failure happens. And that's a result of cyclic loading. So we are somewhere here in this graph. Sometimes we can have infinite number of cycles and failure never happens. This amount of force, which under that one failure won't happen, is represented a point here in infinite life region. So for example, for this type of material, SF here is around 50. So I can say if this force is around 20 kpsi, I'm here, and we have an infinite life, so failure won't happen. There is one point here before I want to continue, and that is about if we have okay, I'm gonna tell that one later. The variables. One of the variables that we have here in the vertical axis is SF, and is SF, and that is fatigue strength. Index F in this chapter represents fatigue. The other things that we're gonna see a little bit later is SE. So that is endurance strength. And we have N here, and N stands for number of cycles. Okay, let's come back to these three critical points. For the first critical point, we said that the number of cycle is 1. That's for this case here. Okay. For all these critical points, we know about the number of cycles. For example, for this one, this is 1. For this one, this is 1,000. And for the last one is 1 million cycle. So we don't have any worries about the horizontal axis value. But for the vertical one, which is log of fatigue strength, or fatigue strength, we are worried, and we need to know about these values here. For the first point, that's easy. SF fatigue strength is SUT. So that's this case. So we know that the failure happens at ultimate strength. For the last point here, this happens for each material at one point. This graph is not for all material, it's just for a specific type of material. But if I want to say in general, this point is something that we called SE. Endurance strength. So SF for 1 million cycle is equals to SE. And this is important for us. We want to know what is SE for each material, for each case. And I'm going to show you how to find SE. For this point, SF is equals to some fracture of SUT. We can find this SUT from web, I'm going to say online, or in some tables like table 820 in the Shigleys, or it will be given to you. We don't have any problem for SUT. So once we found SUT, we can find SF for the first point, and in order to find SF for the second point, we need to know about this F. When we multiply F by this SUT, we're going to find SF for the second point. Okay. And this graph is used when you want to find that fraction. Before I want to continue, this graph, it shows that F based on SUT. For example, if in our studied case, SUT is 170 kpsi, we're gonna go up, find the intersect, then we're gonna go and read the number. So in this case, it's almost 79%. Okay. If SUT is less than 70, so this line will continue like this, horizontally. So for example, if SUT is 50, I'm gonna represent, and I'm gonna say this number as my F. Okay. And if that is more than 200, you can also make a straight line, or you can interpolate something here and try to continue this one. It's not that important. For example, if SUT is 240, you can represent 77%, or 77%, that's fine. Okay. So we don't have any, if I come back to previous slide, here, so I can find this one, and I can find this one. Now the question is how I find vertical value for this point, which is SE. So I want to know how to find SE. In order to find SE, I need to define something which is SE prime. By prime, we mean an ideal, highly polished specimen under just bending loading in completely reverse scenario here. This material can just be found under lab conditions. It's a very ideal scenario. When we know that SE prime, we can somehow find this SE based on that SE prime. The equation that relates SE to SE prime is called Marin equation. And this is Marin equation. SE prime times couple of factors which ended up with finding SE, endurance strength. Actually, if you want to find SE, you need to take that part of machine and you need to take it off and test it and find SE. But because sometimes it's very, very expensive to do that, sometimes it's not practical and you cannot do that. This is why we use these equations when we put all these factors in order to find endurance strength. Okay. So far we know SUT, and if we know SE prime, we can find SE based on SE prime. Here we want to know if there is any relationship between SUT and SE prime, because this part can be found from internet, and if we know this one, we can just put it here and find SE. This question mark can be answered here. That SE prime is very related to, I can say it's all related to SUT. If SUT is less than 200 kpsi, SE prime is half of SUT. In 90% of cases, we are in the first line, and 200 kpsi is almost 400 megapascal. If SUT is more than 200 kpsi, that's I. We are in the second line, so we can just say SE prime is 100 kpsi. And if SUT is more than 1400 megapascal, so if we're in the imperial system, we're going to represent this one for very high SUT, and if we are in SI system, we're going to represent 700 megapascal as our SE prime. So that means that we always divide by 2, but for very, very high loads, we don't divide that one by 2, and we just divide the limitation by 2. So if it's 200 here, it's 100. If it's 1400 here, that's 700. Okay. So we know about this SE prime. In order to find this SE, there are some factors, small k, I, and that's not capital K, small k. Capital K is used for stress concentration, and we're going to see in the future. Ka is surface condition modification factor. For example, if our real part has some scratches on the surface, we need to consider those scratches by applying this factor on our ideal specimen. Kb is a size modification factor, is used for size. Kc is load modification factor. Se prime is for when we just have bending loading. But in reality, we can have bending, we can have torsion, we can have axial, all type of loadings. If we have this case, what we need to do, we need to multiply the Se prime, which was for bending loading, by a factor. So after that, this means that we are considering all type of loading for our real part. Temperature modification factor, which is Kd. This is applied for very, very high temperature, or sometimes for very, very low temperature. Reliability factor and miscellaneous effect modification factor. Usually that's one, we're not that worried about that one. Now I'm gonna go and review all these factors in detail, one by one. So that's Marin factor. This is Marin equation, so we're gonna talk about Marin factors. The first factor is Ka, and that's A times SUTB. In this chapter, it's very confusing. We have so many A's, so many B's. But anyways, we just keep the notation of the book. If you want to find Ka, you need to, we know SUT, you need to find Ka based on this equation, A times SUT to the power of B. This A and B can be found from this table. For example, if we are in imperial system, we are here, and if the type of surface finish is machined or cold drawn, so we are here, this factor A will be 2.7, and the factor B exponent will be minus 0.265. So in this case, that will be 2.7 times SUT to the power of this number. And if we are in SI system, exponent B is the same, but the coefficient here, we need to report that one. Okay, so that's for the factor A. For factor B, let me erase these ones. Okay, and factor B, we said that if there is an axial loading, factor B is 1. But if it's not axial loading, like if this is our specimen like this, and we have different type of loading, based on the diameter, so if that's a diameter, KB can be reported by either of these equations. But the problem is the cross section is not always circular. If it's not circular, if it's something like this, like rectangular or T or I-beam or any other shape, what we need to do, we need to here, instead of using D diameter, we need to use equivalent D. For example, in this case, equivalent D is this coefficient times real D. Okay, if we have this case, we need to find the area, find the square root and multiply by this one, and use this equivalent E here. Okay. KC. KC depends on type of loading. If you have bending loading, that's 1, because SA prime is defined for pure bending loading. If you have axial loading, we need to consider 85%, and we need, if we have torsion, we need to consider 59%. Okay. KD again is temperature factor, so we just need to, that's for high temperature, when F is more than 70 and 70 Fahrenheit, that's important. The unit has to be in Fahrenheit. We're going to put that one here in Fahrenheit, and we're going to find KD, and we're going to put it here. KE is reliability factor. It's interesting, when KE is 1, that means that we have 50% reliability factor. So for example, if you want to have 99% reliability factor, you need to put this number for your KE. This KE is found based on ZA. You can just forget about this line and represent KE directly. Okay, and this KF is for other type of factors, and it's usually 1. Okay, we come back to SN diagram. All this chapter is mainly basically based on this diagram. We said that for this, for at n equals 1, for 1 cycle, SF is SUT. For 1000 cycle, SF is F times SUT. And for 1 million cycle, SF is equals to endurance strength. And we know how to find the endurance strength. Sorry. Here, we are curious to find the equation for the line at this area here. This equation, after doing some mathematics, can be represented like SF equals to A times N to the power of B. Here, this A and B is different from A and B in first modification factor. This A and B can be found based on ultimate strength and indirect strength of my material. Okay, this is a little confusing, but if you are asked to find the fatigue strength for a specific type of cycles, what you need to do, you need to put that number of cycle here and find these two factors based on SUT and SE, and then find SF for that specific number of cycles. Or there is another equation here, and this equation is when you have reversed, completely reversed stress. For example, if your complete reversed stress is something here, you can continue to this point, find the intersect, and read this number. You can find the number of cycles based on this equation here. This is this equation, but in different type of notation, kind of. But whatever you can find here in these equations are not that accurate. They are all approximate. So that's why we have like approximation sign here. Okay. Stress concentration. Always when we have dynamic type of loading, stress concentration has to be considered. In order to if we have a static type of loading, stress concentration is just KT. That we just talked about that before these slides. We can find it from the table. If we have dynamic type of loading, if you want to find stress concentration, we need to find two factors, KT and Q, and combination of these two will give us some factors which is called fatigue stress concentration. These two K's are capital K. So we don't have any questions about finding KT. It's the same way as static type of loading. In order to find Q, which is notch sensitivity, there are two ways. One way is finding Q based on the graphs. For example, if I have a specimen like this and there's a hole in it and there is axial loading like that, if I want to find Q for this material, I know about the radius of this notch here. So what I'm gonna do based on the unit of the problem, if that's imperial, for example, if the radius of that hole is 0.06 inches, I'm at this point, so I'm gonna draw a straight line, and if the SUT of material is, for example, 100 kpsi, I'm gonna find the intersect, which is this point. Then I'm gonna read the number in the y axis. So this is notch sensitivity, and for this case, this is 80%. If I'm in SI unit, if the radius is, for example, 2.5 millimeter, so this is 2.5 millimeter, I'm gonna start from top, and if the SUT of material is 1 gigapascal, I'm gonna find the intersect between the radius and that SUT, and I'm gonna read the number again in the left. So here in this case, that's almost 90%. So Q, one way to find Q is finding from the graph, and this dash line is for aluminum alloys. Okay, for steels, like we use the solid lines. And there are two graphs for that one. One of them is for axial loading that we discussed, and the other one is for shear. Okay, it depends on what type of loading that we have. We're going to use that. The second way to find Q, so the first way was from graphs, and the second way is from equations. Okay, Q can be found from this equation, 1/1 plus square root of A over R. We don't have any problems for the r. This is the notch radius. But what is square root of a? The square root of a is Nuber constant and is a material constant. It depends on the type of loading that we have. If we have bending or axial loading, in the first part we were using the first graph here, square root of a can be found from this equation. So we know SUT, we substitute SUT here, and we're going to find the square root of a based on this equation. And if the type of loading is torsion, in the first part we're going to use the second graph, shear stress, yes. Here we're going to find square root of a based on this equation. So square root of a is a function of SUT. If I were you, I would always use the graphs because that's easier and save lots of time. You just read a number here, you need to apply the number here and but that's up to you. Okay, I'm gonna give you an example here. For example, if I have a specimen under bending moment, so I said I need KT and I need Q in order to find KF. This KT can be found from appendix A15 and A16. For example, in this case, when you have a specimen under bending moment loading at and the hole inside, we need to go to this table. Here, it's second number at this table. And we need to find the diameter of the hole over the width of the specimen. For example, if you find that one and that ratio is 20%, 0.02, we need to draw a straight line. And this one is d over h, diameter of the hole, over the thickness or depth. So if that is, for example, 1, if d is equals h, for example, we're going to report this number, which is almost 185, as our KT, theoretical stress concentration. We don't have any problems in that one, it's like solids. And this is table A16. In table A16, there are two tables, 16A, 16.2. This is 16.2. 16A is for bending, 16.2 is for torsion. For example, if you want to find stress concentration in this point, for this point, you need to find J net, and this is PA over outer diameter to the power of 4 minus the inner one to the power of 4 over 32. D, capital D and small d are given in the question. For finding A, what you need to do, you need to come to this table, and based on A over D and D over D, for example, if A over D is this much in your case, and small d over capital D is that, you need to present these two numbers. The first one is for your A, that you're going to use, and the second one is KTS for shear stress. Okay, so when you want to, for example, when you want to find the shear at this point, the real shear, that will be KTS times T naught. T naught is a normal one. So T naught here, as we discussed, is T R over J. We talk about that in the before these slides, and I can say R is radius, so it's half of the diameter. So I can say T D over 2J, and this is exactly the equation that is shown in the table. It's not that difficult, and this J can be found from this equation. It's just reading a table. I don't want to spend that much time on these ones. You can figure out all the equations is given in the appendix. Okay, once we get KT, and once we find Q, we can find KF based on this equation. KF is equals to 1 plus Q times KT minus 1. Okay, that's an important equation for us. So KT can be found from these tables, Q from another type of tables, and we're done. Okay, the last part of this chapter is about fluctuations. At the beginning of this chapter, when we said that SN diagram is for fully or completely reverse scenario, we mean this case. Here, stress time behavior is something like that. We start from 0, we go to some amount of maximum stress, I'm gonna say tension, then we go to compression, then again tension, then compression, and we hit the maximum amount of each one, tension and compression, like that. And we are fluctuating around time axis. This is called and known as completely reverse scenario. But in real part, we don't always have this scenario. We can have repeated scenario. By repeated, we means that we start from something and we go to fully tension scenario, then we go to 0, then again we go to some amount of maximum, then we go to 0. For example, if I have a specimen like this, if I put bending moment on that, I can have this one as my maximum, then again make it straight, then again go to this one, make it straight, go to this one, make it straight. So I don't go to the other section, I'm just looking at one side, for example at this point. So this point goes to maximum tension because it's stretched, again to 0, tension 0, so that's repeated case. And we can have a general fluctuation types. We can have some offset from time axis, and we can fluctuating around something. We can increase and decrease load. Okay, for example, we have a specimen like this, and there are forces acting all over the specimen, and this force can be varied from 8 kpsi to 68 kpsi, and both are in tension. So that means we are here 18, we can go to 68, go to 18, go to 68, go to 18. So the force is fluctuating and we are not around 0. Okay, this is what we want to study on now. In general fluctuation scenario, there are two parameters that are important for us. The first one is the amount of offset, which is known as mid-range stress or average stress, which is maximum plus minimum stress divided by 2. This is maximum minimum divided by 2. In our case, it was 68. What was the other one? And 68 and 18. So what we need to do, we need to, those were forces, we need to find the stresses by dividing them by surface area, and we just find the average. So this is the average one. Okay. The second one is the amplitude of this oscillation, which can be found from absolute value of differences between maximum and minimum stresses divided by 2. So these two parameters, mid-range stress or average stress and alternating stress or the amplitude of this fluctuating, are important for us. And we can get them based on these equations. Once we get these two equations, we need to plot alternating stress versus mean stress or mid-range stress. There are a couple of important points for us. When mean stress is 0, okay, I'm gonna show again, like we are studying this one. This is sigma m, and this is sigma a. When mean stress is 0, it means that we don't have any offset, so we are oscillating around the x-axis. Okay, so when we are here, so that's a completely reversed scenario. When alternating stress is 0, that means we don't have any amplitude. So that's the static type of loading. There is no fluctuation. Okay. So yield strength is one of the important point for us. If we draw a line between the yield strength in both axes, we're going to end up with a line, and this is called Langer line or yield line. And based on each line, we define a scenario, and based on each scenario, we define or we find a factor of safety. So this is endurance strength. If we draw a line between endurance strength and yield strength, this line will be called Soderbergh line. And we can have different type of scenarios here. When mean stress is 0, so we said that we are in a completely reverse scenario. This endurance strength is more important for us. This is what we discussed about that so far. We discussed about Marin equation, how to find this number. So these scenarios that are starting from this point is somehow more conservative and better than considering Sy as our failure point. Okay. And when alternating stress is 0 here, okay, we can use Sy because that's a static type of loading. So if I come back to my example, I had amount of force was changing from 18 to 68. I'm say that area is 10. Okay, so I can find maximum stress by dividing maximum loading over time, so that will be 6.8. I can find minimum stress by dividing the minimum force over time, so that will be 1/8. Both of them were tension force. If one of them was compression, we had to consider minus here. That was an agreement. When we are compressed, the amount of stress is presented with negative, and when we are stretched, we are positive. Okay. So this is minimum, maximum. I'm gonna find average stress, which is the average between these two, and I'm gonna find alternating stress, which is absolute value of these two. This is easier. That will be 2.5. Okay, yeah, it's 2.5, and here that will be, so it will be 6, 8.6 over 2, 4.3. Let me double check. That will be 5 over 2, 2.5. That will be 8 over 4.3. Okay, so sigma m is 4.3. For example, this is 4.3, and sigma a is 2.5. So this is 2.5. In this case, this is my point, my load point. If I am inside this region, that means that I'm in the safe region, so I'm okay. If my point was something here, that means that I'm not okay. Okay, I'm gonna talk about that one later. But let's say this is one point A. For different type of question, we are here, point B and point C. So we know that point C is not okay. We will not talk about this one. Point A and point B. Which one do you think it's better? And this is point D. Maybe that's easier to discuss between point D and point B. Do you think point B is better or point D? Point B is better for us because this line is like an edge. We are walking around the edge here. It's true that we are studying around the edge, by the edge, but we don't want to walk around the edge. So the far we are from the edge, the better we are. So this point is better. So it should have a better factor of, say, I'm going to talk about that later. Don't want to confuse you. Okay, that's the first thing. If I want to compare these 2 points, point D based on Langer criteria is a safe point, but based on Soderbergh is not safe because it's out of the region. Okay. So Soderbergh is very conservative in comparison with Langer line. And okay, I'm gonna remove these ones. Okay, modified Goodman is not exactly the area covered by this line, area with triangle. Um, it starts from this point in runs to the intersection of Langer and Goodman line. Then it follows the Langer. So this area is modified Goodman. So we modify Goodman and we found this area. So for example, if my point is here, based on modified Goodman, it's not in the safe region. So we have to be here. Okay. So don't confuse with this title here. I should have put that one somewhere, maybe here. Anyways, and these are the other criteria: Gerber line and ASME elliptic line. So ASME, this line, as it is shown in the name, it's an elliptic equation, and Gerber line is a second order equation, a parabolic equation. This is the other one. And these two criteria are very good if you want to use your design based on these two. I suggest you to do that in real life. But the problem is finding equations for these two are very difficult. So maybe it's not a good idea to explain it here. But anyways, the problem with these two are it's difficult to find the equations, but they are very good criteria to use. So if this is our point A, load point, we can draw a straight line between origin and the point, and that line is called load line. So this is load line. Okay, so slope for the load line, if that's my load line, this is rise over run. Rise is SA, run is SM. If this is theta here, I'd better say slope is tan of theta, and tan of theta is rise over run, and this is the slope. Okay, if my case was not this point A, this point A is not a good point for presenting at this slide, because the intersection between this point and this line is occurred on the line, on the load line. If I have a load line like this, these are the important points for me. The intersections of the load line and each criteria, because we're going to define some safety factors, some graphical safety factors based on the distances, these distances. Okay. If my point line was this green point here, okay, so there is no intersect between this point and any of these criteria. If I draw a line from SUT passing our load point, the intersect between that line is not called load line, that line and alternating stress is going to give us reverse stress, and that's a completely reverse stress. If you want to find completely reverse stress based on a diagram, which you are asked in your question, your problem, your tutorial problem last week, you need to draw a line here and you need to report this number. Okay. Safety factors. Based on each scenario, we're going to have one equation. For example, if you want to find safety factors based on Soderberg, this is safety factor. We have sigma A, sigma M, we have endurance strength, and SY yield strength, we can find N. If we want to use ASME elliptic, we know sigma M, we know this one, everything but N. So N can be found from each of these scenarios. Okay. Sometimes we have a combination of loading on a specimen. In those cases, instead of finding sigma A and sigma m, we need to define sigma A prime and sigma m prime. In order to find that, you can use these two equations, and there are some factors, and when you multiply those factors by the type of loading that you have, you're going to find an equivalent sigma A alternating and mid-range stresses, and then you can just use that one and plot your sigma A prime, sigma m prime, and do what we did for the previous step. Okay, if you have any questions, feel free to comment below. Before I want to finish this one, I'm gonna I'm gonna have a quick review about what we covered in these slides. Okay. Oh, yes, keep them, why not? Okay. Okay, we said that everything starts from internet, from online, or from table A20. And again, I'm saying that all the tables and graphs that I'm going to mention now is based on 10th edition of Shigley's book. And if you haven't bought that, maybe it's a good idea for you to pause the video and find the book somewhere online, or order it from a website and get a textbook. Okay, from this table, what we can read is ultimate strength or yield strength. For some materials, yield strength at tension and compression are different, but these are the material properties that we can find from. This is for steel, I believe, maybe a steel 1820 or 1810, but we can find those parameters. When we find that one, we need to find SE prime. SE prime is endurance strength for an ideal specimen. In order to find that one, you can use equation 6.8. So equation 6.8, maybe I can write it here. Equation 6.8 is related SE prime based on that. So SE prime is a function of SUT. Okay. So when you get SE prime, you need to find endurance strength. And here you need to use equation 6.18. And so SE is a function of SE prime, and this equation is called Marin equation, and we have a couple of factors here. Okay, we have Ka that can be found from equation 6.19 and table 6.2. We have Kb that can be found from equation 620 and 621 and table 6.3. We have Kc that can be found from equation 626. We have Kd that can be found from equation 627. We have Ke that can be found from table 6.5, and Kf, which is other factor, which represent for other factors. Okay, so when we get these SE based on Marin equation, so these are Marin factors, we're gonna check something here. No, we're gonna check a stress concentration. Okay, let me take these ones. Okay. We're gonna check stress concentration. If the material, there is no notch, no radius, no fillet, no hole in it, so we are in the no part. But sometimes, and I'd say most of the times, there are some stress concentration sources in the material. So this is, for example, this is for a material like this, and this is for a material, the stress concentration. If there is any stress concentration sources, we need to find KT, that's capital K, theoretical stress concentration, and this can be read from A15 and A16 appendix, table 15 and 16 in appendix. And we need to find notch sensitivity, Q, and this can be found from table 620 or 621 and 621, or equations 634 and 635. So there are two ways to find this Q. You can use whatever you want, and once you get that, you're gonna find KF based on these two parameters. Okay, so if there is no stress concentration, we jump to this step, but if there is some stress concentration, we need to do these parts and find those, KFs. Okay, so I'm gonna say so after this point, we're gonna find maximum and minimum stresses. Maximum is F max over the area, minimum is F mean over the area. Area could be different in different questions. And once we get these stresses, we're gonna find mid-range or mid-range or average stress, which is sigma m and sigma a, and this is equation 636. And when we find that one, it's done, plot. So we can plot sigma a versus sigma m, and if you are asked to find safety factors, can be derived from 645 to 649. Okay, there is one thing here. When you find this safety factor, fatigue safety factor KF, we need to somehow use that, and I'm gonna bring that one to your attention at this page. For example, if our mid-range stress can be found from this equation, the average of mean and max stresses, this is for a specimen without any hole. If there is any hole, or for example, if there is something like fillet in the specimen, like this is the fillet with a radius of r, we're gonna find a fatigue safety factor, fatigue stress concentration, and we're gonna multiply that one by the whole fraction. And the same thing happens for alternating stress, so that will be KF times maximum stress minus minimum stress divided by 2 absolute value. And we're gonna plot sigma A over sigma M for these evaluated numbers. I think this chapter is covered, maybe 80% of this chapter, 90% of this chapter. And if you have any questions, feel free to ask. Send me an email at engineeringfun2016@gmail.com. And okay, so in part, this is a better review here. And SA, SE, these Marin factors are shown here in these notes. What is KH, what is KB, KC, KD, how you can find that, we talk about that, how we can find KF, what is square root of A, these equations, and we said that these A and B are different from A and B in KA, okay, I think this pen is tired. KA is A SU T to the power of D. These A and B are different from these two. These are found from a table based on material properties as safety factors for each scenarios. And yeah, everything is almost covered in these notes and in these slides. I hope it can help you study this chapter better, and I hope it can answer the questions that you had in your mind. Okay, thank you for your time.